Okay, so let's start. So, so welcome to Algebra 1. This is noc22 ma59 offered by NPTEL, and this is week 9. So I am one of the PMRF TAs for this course. My name is Shubhajit Das, and hope you are also attending Harish's sessions. Those happen on Friday. So as we do every week, we solve some problems. So these are based on the problems of the previous year assignments. Okay, so let us start. So this week you have learned more on module theory. So you have seen homomorphisms of modules, quotient modules, etc., etc. So the questions will be briefly based on those concepts. Okay, so let us start with the first problem. Okay, so let us read out the question first. So which of the following are true for the function f from z adjoined with root 2 to z adjoined with root 2, which sends a plus b root 2 onto a plus b. Okay, so we are given this function of this map, and we need to figure out which of the following statements a and b are actually correct for this function. Okay, so see. So the first option is that f is a z root 2 module homomorphism, and the second one is that f is a z module homomorphism. Okay. So since the scalars in z are there are lesser number, so to say there are lesser number of scalars in z as compared to z root 2. Let us first investigate the case of z, I mean z linearity. Okay. So first of all, observe that. So observe that if respects addition. So indeed f does respect addition, there is no doubt about it. So we need to check whether it also respects z linearity or not. Okay, so for any scalar n in z, f of n times a plus b root 2 is f of na plus nb root 2. Now clearly na and nb are integers, right? So this is just na plus nb, which is n times a plus b, which is n times f of a plus b root 2. So indeed, so this is true for all a plus b root 2 in z root 2 and for all in z. Hence B is correct. So option B is correct. Okay, so option B is clearly correct. There is no doubt about it. Now what about option A? So we don't even need to check here anything. I mean, it just we can just observe something and conclude. Observe that if f is a, suppose A is a ring and you are given modules, A modules M and N, and suppose you take a mapping A module homomorphism from M into N, then the image of F is clearly a submodule, right? It's an A submodule of N, right? But since f of z root 2, that is the image of f, is contained in z, which is contained in z root 2, and and f of z root 2, the image is non-zero, hence the image of f, that is f of z root 2, is not a submodule, right? Is not a z root 2 submodule. Of it's not a Z root 2 submodule of Z root 2. You can consider here we are considering Z root 2 as a module over itself. So it's clearly not a Z root 2 submodule of itself. Hence, A is not correct. So let me just to be very precise, let me just write not in caps. So certainly option A is not correct, option B is correct. So B is the correct option. Okay. So here we have something that if the map that we are given here, it's a Z module homomorphism. It's clearly Z linear, but it's certainly not Z root 2 linear, right? Okay. So let's move on to the next problem. Okay. So question 2. So let us read it out. Let R be a commutative ring with a 1, and let F mapping R cross R into R be a map, any map, just any map. Then F is an R module homomorphism if and only if we can find elements A and B in R such that F of xy is Ax plus By for all xy in R. Okay. So by an R, so when we are saying that F is an R module homomorphism, this means that we are endowing R cross R with its usual R module structure, and R is also, as we know, is an R module over itself. So R cross R or R both are actually called free modules over R. These are free modules over R. That is modules which admit a basis over the base ring. Okay, so we need to figure out whether this statement is true or false, that the map F that we are given, it's an R module homomorphism if and only if there exist two elements A and B in R such that F of xy is this for all xy in R. So first of all, so we claim that this is a true statement. So suppose there exists A and B in R such that f of xy is equal to Ax plus By for all elements xy in R. We claim that F is actually an R module homomorphism in this case. So then f of xy plus x prime y prime is just f of x plus x prime comma y plus y prime, the usual group structure on R cross R, which is equal to, so this is equal to what? So this is equal to a into x plus x prime plus b into y plus y prime, right? So this is ax plus by plus ax prime plus by prime, which is just f of xy plus f of x prime comma y prime for all xy comma x prime y prime in R cross R. So clearly F preserves the addition of R cross R, and also for any so for any R in R, f of R times xy by definition is f of Rx comma Ry, the usual module structure on R cross R. So this is equal to, I mean the scalar multiplicative structure, R scalar multiplication on R cross R. So this is just A times Rx plus B times Ry, right? And since we know that R is a commutative ring, we can just take R in the beginning and use the distributivity of multiplication over addition. So we get this, which is R times f of xy for all xy in R cross R, right? So that means F is R linear, or it's an R module homomorphism. So what about the converse direction? Suppose indeed that F is an R module homomorphism. So we need to figure out whether F looks like this or not. So conversely, assume that F is an R module homomorphism. Then for any x comma y in R, we know that, okay, so before that we just use symbols. So we define A to be the image of 1 0 under F, and B to be the image of 0 1 under F. So both are elements in R, and for all x comma y, so for all x comma y in R cross R, right, uh, f of x y is f of x times 1 0 plus y times 0 1, right? And now you are using the fact that it's an R module homomorphism. So x times f of 1 0 plus y times f of 0 1, which is therefore equal to x. Okay, so I'm sorry. Yeah, it really doesn't matter because everything is in R. So yeah, so xa plus yb, which is, we can write as ax plus by, right? Since we started with a commutative ring. So yeah, we have this form. So that finishes the proof. Okay, so every element is indeed of this form. I mean, the image of every element xy under the map is precisely ax plus by for all xy in R. We have found two fixed elements a and b in R, such that for every xy in R, f of x comma y is ax plus by. So indeed the statement is true. It's an if and only if statement, and this is true. So this, before we move on to the next problem, just a small thing to say is that um, this is precisely why I was stressing on the fact that R cross R is a free R module, right? That is, in other words, it's a module over R which admits a basis, right? And you know that to define a homomorphism from a free object into some into a like object, right, into an object of the same kind, what you need to do is define the images of the basis elements, right? So this is the universal property of a free object, right? That you have an object is free on a set means that for any object of the same kind and any map or any morphism from that set into uh, this new object, any such map can always be extended on the entire free object, right? So that is what is happening here. 1 0 and 0 1 is precisely an R basis of R cross R. Okay, so let us move on to the next problem. So observe, or maybe consider Q and Z as Z modules, right? We know that every abelian group is a Z module, so Q and Z in particular are Z modules. So we need to find the number of Z module homomorphisms from Q to Z. So we need to find how many Z module homomorphisms are there from Q to Z. Okay. So we claim that there is exactly one such homomorphism, namely the trivial map. So let F mapping Q into Z be a Z module map. So let A be in q minus 0. Okay. Now we are basically going to solve this. We are basically going to use a very specific property of the z module q, namely that q is something called a divisible z module, right? It's something called a divisible module, which means precisely that if you take any non-zero integer n, and if you take any element of q, let's say a, then you can find a b in q such that n times b gives you a. This is what we mean by as divisible module or a divisible abelian group in this particular instance. Now q is divisible, but z however fails to be divisible, and that is what we are going to exploit here. Okay. So the point is, then for any integer n greater than equal to 1, f of a is equal to n times f of a by n, right? This is precisely because f is a z module homomorphism, so n times f of a by n is just f of a, right? So, and this is an equation, so this is an equation in z, right? This is an equation in z because the target is z, right? The target of f is clearly has been taken to be z, right? So which implies that n divides fa in z for all for all integers n greater than equal to 1, right? For all integers n greater than equal to 1, right? Now if n divides fa is an integer, and if n divides fa for all integers n greater than equal to 1, what does that mean? Clearly fa cannot be some non-zero integer, right? Because if it were some non-zero integer, then it would have a finite number of prime factors, right? But here every integer in every integer greater than equal to 1, in particular every prime number divides fa, right? So this basically implies that f of a is equal to 0, right? So the reason is that every non-zero integer has a finite number of prime factors. Right? So we started with a non-zero element a in Q, and we saw that f maps a to 0, right? Which precisely means thus if a is equal to 0 for all a in Q, in particular 0 always goes to 0, right? Under any homomorphism. So hence under any module homomorphism or group homomorphism, whatever. So hence f is equal to 0, right? Thus the number of mappings of Q into Z, which preserve the Z module structure, Z module homomorphisms, of Q into Z is 1. Right? So the answer is 1. We only have the trivial homomorphism. Okay. So let us move on to the next problem. So let us read it out. So suppose that f mapping m into n is an R module homomorphism that can be written as this composite. So you have an arrow from m to p, which is u. You have a morphism of p into q, which is v, and you have a morphism of q into n, right, w. So the arrow f can be written as a composition of 3 arrows, which are written here, where u is a surjection. So the first one, m to p, the arrow u from m to p, this arrow is a surjective homomorphism, R module, surjective R module homomorphism, or in other words an AP morphism. V is an isomorphism of P onto Q, while W is an injective homomorphism from Q to N, right? That is a monomorphism from Q to N. Okay. So we are given these three arrows, and we know that their composition is F. Okay. So we need to figure out whether the following statement is true or false. P is isomorphic to M mod kernel of F, and Q is isomorphic to the image of F. So the module P is isomorphic to M mod kernel F, while the module Q has to be isomorphic to the image of F. Now this is true, there is nothing wrong with this, and the point is that this is in fact true in a much more general context uh, than the uh, case of modules. We are working with modules, but modules are sort of, what should I say, they are examples of a very general kind of object in a very general world where the same kind of phenomenon actually happens. Okay, so in particular this is right, there is nothing wrong with this. So we can prove this very easily. So the point is that so the statement is true. Okay, so how do we prove this? So F is equal to W composed V composed with U, right? Now U has been given to be surjective, that we know. Okay, so since V and W are injective, they are monomorphisms in particular. V is an isomorphism, hence in particular an injection. W is clearly given to be an injection, hence W composed with V is injective. Thus F is equal to W composed with V composed with U, and this is an injection, implies that you can check this, that the kernel of U is equal to the kernel of F. So basically, as you know, what do injective homomorphisms do, right? They always map non-zero elements onto non-zero elements. They have trivial kernel, right? So whenever you compose some arrow, I mean post-compose some arrow with some injective map or some monomorphism, so there is no change in the kernel, right? The composition has the same kernel as the original map. That you can easily check. So now what we do is we apply the first isomorphism theorem. Theorem on the surjection M to P U to get M mod ker U, or rather let me just write M mod kernel of F, which is the same as M mod kernel of U. It's isomorphic to the U of M, which is equal to P, the image of U, which is P. Precisely because U is surjective, right? Thus M mod kernel of F is isomorphic to P. That we have proved. And what about the other one, that Q is isomorphic to the image of F? Again we use this the sort of dual argument here, right? So we did for injections, now we do the same thing for surjection. So since U and V are surjective, hence V composed U is surjective, right? That is V composed U, this arrow V composed U, which maps M into Q, is actually a mapping of M onto Q, right? It's a surjective mapping of M into Q, and in fact onto Q. So yeah, so V composed U is surjective. So what is F? F now is W composed with V composed with U, and since V composed with U is surjective, the point is that the image of W is precisely the image of F, right? So hence F is equal to W composed with V composed with U, and this is given to be surjective, which implies that the image of F is equal to the image of W, right? They're the same. The image of F is the same as the image of W. And finally, since W is injective, we know that W is a mapping of Q into N, that we know. W clearly maps Q into N, right? So we know this, that W is a mapping of Q into N, and moreover we know that W is injective, which means that Q is isomorphic to W of Q, right? Q is isomorphic to W of Q. That is, this is just the same as, I mean, this is precisely your image of W, right? W of Q is the image of W, which is equal to image of F, right? So this Q is isomorphic to image of F, and which is precisely our second statement, and therefore we are done. Okay. So this statement is indeed true. Okay. So let us move on to the next problem. Okay. So we need to find out the number of Z module homomorphisms of Z mod nz into Q, right? So Z mod nz is an abelian group, hence a Z module. Q is an abelian group, hence a Z module. And we are taking a mapping of Z mod nz into Q. We are taking a mapping. We are considering mappings of Z mod nz into Q, which preserve the Z module structure. That is, which are precisely Z module homomorphisms or abelian group homomorphisms. Okay. So again, we claim that there can be exactly one such map. So let F map Z mod nz into Q. Okay. So observe that Z mod nz as a group, or as an abelian group, or as a Z module is can be generated by a single element, right? Namely 1. 1 generates Z mod nz over Z. So yeah, so there's no. So then F of class of 1 times n times this is F of class of n, right? Which is F of 0, which has to be 0, right? And this entire thing is happening in Q, right? In the rationals Q. So n times F of this is 0 in Q, and Z is a subring of Q, as we know. We can consider now the ring structure on Q. So F of box 1 is in Q, n is also in Q, and their product is 0. Now Q we know is an integral domain clearly, which implies, okay, so we mentioned something here. Yeah, I should. So n is greater than 0. Yeah, that's clear, right? Whenever we say Z mod nz, we always mean n greater than 0, because congruence relation is only applicable when n is strictly greater than 0, an integer. So n times F of box 1 is 0, implies that F of box 1 has to be 0, right? Thus F of box K is F of K times box 1. This is where we are using the module structure of Z mod nz over Z, the fact that it's generated by the class of 1, right? So this is K times F of box 1, right, which is precisely 0. So F of box K is 0 for all box K in Z mod nz, right? Hence F is 0. Thus the number of Z module maps fisms of Z mod nz into Q is 1, right? That is the trivial map. So this was a very simple problem. Okay, now we move on to a very powerful, very important concept in algebra, in particular in commutative algebra. And yeah, so this is the notion of an exact sequence. So a sequence of R modules and homomorphisms as given here from U1 is from E1 to E2, U2 is from E2 to E3, U3 is from E3 to E4 and so on, is called an exact sequence whenever the image of uj is equal to the kernel of uj plus 1 for all j in 1 2 3 and so on up to n minus 2. That is, in other words, so let's say you have a simple sequence a to b to c of groups, let's say, or of r modules, let's say f g. This sequence is said to be exact at b, or we only check exactness at intermediate modules, okay, not at the extreme ends. So this is called an exact sequence, or this is said to be exact at b if the image of f, so the image of f is equal to the kernel of g. Image of f is a submodule of b, kernel of g is also a submodule of b, and they have to be equal, right? So then this sequence is said to be exact. And the definition given here is basically when you are uh, sort of concatenating this small sequences to get this large sequence. Okay, so we need to figure out which of the following statements are correct. So first one is that you are given a sequence 0 to e to f, and you are said that this sequence is exact if and only if u is injective. Okay, by 0 I mean here just the trivial module, and 0 to e is the unique map, right? You know that there will exist a unique z module homomorphism from 0 into e, right? So the 0 module clearly has this property, right, that it's for any given any module there is a unique map from 0 to that module, and given any module there is a unique map from that module to 0, right? So 0 is something called an initial as well as a terminal object in the world of modules, right? Or in other words, it's called a 0 object in the world of modules. So anyways, so 0 to e, this is that unique map from 0 to e, which comes because of the fact that 0 is an initial object, and the in option B we have written a map f to 0, that map is a unique map from f to 0, which exists because 0 is the terminal object. So anyways, this is just jargon for the time being. We don't need to get into all this. Let us just figure out which of the following statements are correct. So let's see. So option A, that this sequence 0 to e to f is exact if and only if u is injective, A is true, or A is correct, as 0 to e to f u is exact if and only if the kernel of u is equal to the image of this arrow, right, and which is 0, right, which is true if and only if u is injective. So A is clearly correct. What about option B? We are given an arrow from E to F and we are given an arrow from F to 0. This sequence is exact if and only if V is surjective. So option B is again correct, as E to F to 0 V is exact if and only if the image of V is equal to the kernel of this unique map from F into 0, right? This unique arrow or morphism of F into 0. What is the kernel of this? This is precisely the 0 map, which is F. And this is true. Image of V is equal to F if and only if V is surjective. Okay. So what about option C? So if f is a submodule of E, then 0 to f to E mod f to 0 is exact, where I is the inclusion and pi is the quotient map from E into E mod f, right? Pi is precisely the quotient mapping of E onto E mod f. It's the canonical surjection of E onto E mod f. So we are given I the inclusion of f into E and pi the quotient map of E into E mod f. Okay, so we are given f is a submodule of E, right? So using part A, using A and B, we know that clearly the inclusion is an injective map and pi that happens to be a surjective map, right? The canonical surjection of the quotient map is a surjection. So we know that 0 to f, right? 0 to f to E I and f, sorry, E to E mod f to 0 pi are exact, as I is injective and pi is surjective, right? As I is injective and pi is surjective. Also f to E mod f I pi is exact, as image of I, which is f, is also the kernel of pi, right? The kernel of pi is precisely f, right? Hence 0 to f to E to E mod f to 0 I pi is exact. So option C is correct as well. What about option D? So if U mapping E into F is an R module homomorphism, if U mapping E into F is an R module homomorphism, then the following sequence 0 to the kernel of U to F mod UE to 0, where I and pi are again your canonical maps. I is the inclusion and pi is the canonical projection or the canonical surjection of the quotient map. This particular sequence that we have is exact. So option D is correct as well. So let me make some space. Okay. So again, using part A and part B, right? We know that 0 to kernel of U to E and F to F mod UE, which is called the co-kernel of U. So this is pi to 0 are exact. So yeah, and also kernel of U to E to F mod U of E. So this is pi, this is I, and this is U is exact, as the image of I is equal to kernel of U, which is the kernel of U, and the image of u, which is u of e, is equal to the kernel of pi, right? Exactly. So this sequence that we have is exact at the object e, right? And it is exact at the object f. It is exact at e and at f, which means that this sequence is an exact sequence. Hence 0 to f to e mod f to 0. Okay, I guess I missed something. Yeah. 0 to kernel of u to e to f mod u of e to 0, right? So this is I, this is pi, this is u, is exact. So all four options are correct actually. So A is correct, B is correct, C is correct, as well as D is correct. So exact sequences are very important. They are very important. The notion of an exact sequence is very important in algebra. Okay. So we move on to our final problem. But before we do that, so this is about a notion, a very useful notion in module theory, which is the notion of an inverse limit. So let me just read out the problem first and then I'll say what I wanted to say. So given a collection of R modules, so you take any collection of R modules, let's say mi, indexed by natural numbers, and we are given R module homomorphisms from mi plus 1 to mi. Let's call those mappings of mi plus 1 into mi fi. Okay. So we define the inverse limit of this system. This is called an inverse system. The mi's together with this connecting maps fi, mappings of fi is a mapping of mi plus 1 into mi, right? So this system is called an inverse system, and we define the inverse limit of this system denoted as this limit. You take an arrow in the opposite direction mi fi. We define it to be as follows. It is precisely the set of all elements in the product of the mi. So it's an n index tuple mi, little mi, belonging to product of mi's, such that fi applied on mi plus 1 gives you mi for all I natural numbers. Okay, so this is how we define the inverse limit, and then we are asked to figure out whether something is true or not. But before we move on, sort of get into the problem, what I want to say is, so far in mathematics you have seen a number of different objects, right? So you have seen, let's say you have seen free groups, you have seen, I don't know if you have seen free modules, but you have certainly seen free groups. Then you have seen kernels, then you have seen, what else have you seen? You have seen construction of the field of fractions of a ring, right? I mean of an integral domain, right? And so on. You have seen various kinds of objects so far. Similarly, this inverse limit is also a kind of object or type of object. But the point is that whatever objects I mentioned are actually governed by some universal property, right? They are characterized by some universal property. So for example, let's say even if you forgot how the free group generated by a set S looks like, you can always sort of, even if you forget its internal description, you know its definition because of its universal property. You know that there is something satisfying that universal property, and there will be exactly one such object satisfying the universal property of a free group. Maybe you won't be able to figure out what the elements internally look like, but you always know what that object is from an external point of view, right? That is how, based on what are its relationships with other objects, what are the relationships of a free group with other groups, right? So the point is that the inverse limit of a system of modules as given here also has a certain universal property. Okay, so since we have some time, let me just briefly say what that universal property is, and then we can solve this problem. So let me make some space. I don't know if So I'll keep one page for this maybe. So we just write it down. So let's use, okay. So inverse limits, okay. So let mi I in n, okay. We don't need, we have mentioned that I belongs to natural numbers. The collection of modules is indexed by natural numbers, but we don't need natural numbers for this, okay. We can take any directed poset for this purpose, okay. So but since the definition here has been given for natural numbers, for collections of modules indexed by natural numbers, we focus on this only, okay. So but we can always talk about we can always use directed sets instead of just natural numbers. We can always use directed sets. Anyways, so let mi I in natural numbers be a family of modules, or let's say R modules, and let if I map mi plus 1 into mi be an R module homomorphism for every I in natural numbers, okay. So I guess I have written the notation correctly, right? Yeah. So we are given this family of modules. So mi together with fi I in natural numbers is called an inverse system of modules indexed by n, which as I said can be in fact any directed set. So indexed by n, then the inverse limit of this system mi fi I in n is an R module, let's say we write the notation we use here is this is an R module together with sorry, so it is an R module together with R module maps together with R module homomorphisms, right? Together with R module homomorphisms from the limit I in n mi fi into each mi, okay. Let's call this ui or okay, so mj we are saying, let's call this uj, okay, for every j in natural numbers, such that, so together with R module homomorphisms for all j in natural numbers, such that this particular pair, this object, that is this inverse limit together with these arrows, is universal, okay. It's universal among all such objects and arrows from the objects to the modules mj, okay. So what I mean by this is it's terminal among all such objects. So let me just say it precisely, such that the following universal property holds. that is given any R module, let's say M, okay, and homomorphisms, so R module homomorphisms, that is given any pair M together with this homomorphisms Fi. So given any R module M and homomorphisms, let's say Gi mapping M into Mj, right? Okay, so yeah, yes, so yeah, so Gi mapping M in, sorry, Gj mapping M into Mj, right? Okay. Yes, I forgot to mention one thing here, right? That the inverse limit is an R module together with R module homomorphisms. Yeah. So I should mention one thing. I forgot to mention that. Okay. Such that so the inverse limit of Mi is an R module limit this object together with R module homomorphisms from the limit to Mj for all j in n, such that each of the small triangles will come in. So what I mean by this is, so you have this object, this limit object, this inverse limit, and you have a map to Mj. Also you have a map to Mj plus 1, right? And you know that you are already given a map Fi from Mj plus 1 to Mj. So this triangle that you obtain should come in. So what I mean by this is such that so yeah, such that if j composed with uj plus 1 is equal to uj, right? So you have an arrow from this to mj, from this to mj plus 1, yes, so uj plus 1, yeah, so this is equal to uj for all j in natural numbers. This should hold, okay, such that this holds, and such that the following universal property holds, okay. So what do I mean by this is that and such that the following universal property holds. So what I mean by this is that, so you are given, so the so you have this limit object and you have arrows to this to the modules that you are given to the modules mj, such that each small triangle commutes, as I have said, and such that this particular what should I say, this object together, this limit object together with this arrows, such that all these triangles come in. This is universal among uh, all such objects together with arrows into the various images, such that all the small triangles come in. So to be very precise, what I'm saying is that given any R module M and homomorphisms from Gj from M into Mj, such that the commutativity again holds. That is such that, so again here you have a module M and you have maps M to Mj, right, to each Mj. So again you have a map to Mj, again you have a map from M to Mj plus 1, and there is a given arrow from Mj plus 1 to M, right, that we know, that which is precisely your Fi. So this triangle that you obtain should commute, okay, commutes. So such that, so given any R module M and homomorphisms Gj from M into Mj, such that this triangle commutes, that so what we have here is Gj plus 1 if j applied on that, so composed with that, so if j composed with Gj plus 1 is equal to Gj for all j in natural numbers, okay. So given any such R module sorry, so given any such R module M and given any homomorphisms from given any homomorphism Gj from M into Mj, such that all these small triangles commute, there exists a unique, so there should exist a unique map or a unique R module homomorphism So just observe the picture. You have the limit object here and you have this M here, right? So you should have an arrow from, unique arrow from M to this limit object. There is a unique R module homomorphism. let's call it G from M into the limit object mi comma fi, such that so I'll just draw the picture after this so that it becomes very clear for you what I'm trying to say. So such that uh, so you have this G and you have this uj, so G uj, right? So G uj later, so such that uj composed with G is equal to gj. That is, in other words, there will exist a unique arrow from M to this limit such that each gj factors through the uj's via this unique arrow G. Okay, each small triangle will come in. So for all j in N. Okay, so let me give a picture so that you understand it much better than what I'm saying. So here is your picture. So you have this mi, let's say mj, let's say you have this mj plus 1, let's say, right? You have this mk, let's say, and whatever. So you have this entire collection of objects, and the limit is an object. The limit is an object together with arrows to each such object. Yeah, so before we talk about the limit, in this given collection of objects mi, you are given these arrows, right? If I, so let's say you have an arrow from this to this, this to this, right? Let's say from this to this. Okay, so let's say you are given these arrows and so on and so forth. Okay, so so the limit is an object together with arrows to each mi, right? So maybe it would be better if I use a different color for this. So yeah, so limit I in N mi comma fi, right? So this is an object together with arrows to each of this, right? Such that given any object, let's say, such that all these small triangles will commute. These arrows are given, red arrows, such that all the small triangles are given. So in particular, you have this triangle, right? From limit to mj plus 1 to fi and limit to mj, you have this collection of arrows. So if I compose with this, yeah, let me just name these arrows. So this is uj, this arrow is uj plus 1, and so on, right? All small triangles will commute, and such that given any object M together with arrows into the various mj's. So let me use a different color now. So given any object M together with arrows into the various mj's, right? So yeah, it's getting a bit dirty, I understand. So on. So let's call these arrows, so these are our arrows gj, right? Gj M to mj. Given any, so given these arrows, so gj plus 1 and so on, given these arrows, such that again the small triangles will commute, right? So there will exist a unique arrow so there exists a unique arrow. So given any M and given any arrows gj from M into mj, such that all the small triangles will commute, we will get a unique arrow from M into the limit, right? such that all the triangles that we obtain here will commute. Okay, so this arrow that we have is G, right, such that G composed with, or maybe not G composed with, such that yeah, so we apply Uj later, right? So Uj composed with G should be composed with G should be Gj for all J in natural numbers, right? So G, there exists a unique G, there exists unique G. So this is precisely, this red object together with these red arrows is precisely called the inverse limit. Okay, it's called the inverse limit of the family of modules mi together with the connecting maps fi. Okay, now this is the universal property, and as is true for every object with a universal property, you can check that two objects, I mean you can check that if there is another object that you take that also has this same property, that this red object, limit object satisfies, then it will also be a limit object, it will also be an inverse limit. In other words, these two objects will always be isomorphic. Okay, and what I wanted to say is so what did I want to say? Yeah, so so the point is, this is an external description of the inverse limit, right? This is not an internal. You don't know yet what this module, this red module, limit module, this inverse limit, what this looks like precisely, right? We don't know as of yet. So the next problem is basically giving a description of it internally. But as I said, to know, I mean, knowing the universal property, knowing the object externally, knowing how it interacts with other modules, for example the yellow module M here, knowing how it interacts with other modules is enough to characterize this module, right? So but still, just for concreteness, we just look at its internal description, and that is precisely how I mentioned. Okay, so this limit object is precisely the set of all families or n tuples, n index tuples mi in the product, such that fi of mi plus 1 is mi. Okay, so it's basically a collection like this. So m1, m2, any arbitrary element in the inverse limit looks like this, such that f2 should map m2 onto m1, f3 should map m3 onto m2, and so on. Okay, this is precisely how an arbitrary element in the limit looks like. Okay, okay, so yeah, so now we are given this problem, so we need to figure out whether the following statement is true or false. Okay, so consider each module mi to be z. Okay, z that is considered as a z module, as an abelian group for every I in natural numbers, and we also need this connecting mappings of mi plus 1 into mi. So fi, which maps mi plus 1 into mi, that is which maps z into z, is just multiplication by 2, that is it maps n onto 2n. Okay, so we need to find out whether this statement is true or false. Okay, that this limit z fi, this limit object, is a finite set or not. That is what we need to figure out. So I forgot to write true or false here. So yeah, so option, yeah, sorry, so option A is true and option B is false. So we need to figure out whether this statement is true or false. Okay, now we do indeed have the internal description, right? We do indeed know how it looks internally, so we need to figure out whether this is a finite set or not. Okay, so let n1, n2, n3, sorry, let n1, n2, n3, n4 and so on, let this be an element in the inverse limit. Let this be an element in the inverse limit. Okay, then we know that if I of ni plus 1 has to be ni, right, for all I in natural numbers, which implies that fi of ni plus 1 is 2 times ni plus 1, is to be ni for all I natural numbers, which implies that n1 is equal to 2 times n2, which is equal to n2 again is we are basically having a recurrence relation here, right? So n2 is 2 times n3, right? So 2 times n2 will be 4 times, or let's say 2 square times n3, which is equal to 2 cube times n4. Again n3 is 2 times n4, so this is 2 cube times n4, which is equal to 2 to the power 4 times n5, and so on, right? It goes on, right? So this implies that 2 square, 2 cube, 2 to the power 4, or let's say we just write it in general, this implies this, everything is happening in z, which implies that 2 to the power n divides n1 for all n greater than equal to 1, right? 2 divides it, 2 square divides it, 2 cube divides it, 2 to the 4 divides it, and so on, which therefore implies, since any integer, non-zero integer, can have a finite number of factors, okay, right? In particular, it should have a finite number of powers, finite number of what should I say, there should be highest power of 2 dividing that integer, right? Non-zero integer, right? So that means n1 has to be 0, okay? Hence if n1 is 0, hence n2 is also 0, n3 is equal to 0, n4 is equal to 0, and so on, right? Thus, in other words, what we can say here is that limit I in n z comma fi, this object, the inverse limit is actually to the 0 module, right? It's trivial, so that it's a finite set. And then we are done. Okay, that finishes the proof completely. Okay, so that's it from my side for today. Okay, I hope you understood things properly, and yeah, so this concludes the stuff of week 9. So see you next week, and please do attend Harish's sessions. They happen on Friday. Okay, so please do attend them. Okay, so see you next week. So let me stop the recording.